This lesson, we're going to be talking about non-linear regression. So we'll just jump in with an example and we'll practice some pieces from last class and then we'll move forward with the new information. So we'll start with this first example. So what we want to do is we want to use this data to complete a linear regression to determine if there's a correlation between the year and the percentage of 15 to 19-year-olds who smoke. So we have our independent variable, our years, and then our smokers percentage as our dependent variable. And what we want to do is we want to do our linear regression. So first step, highlight my data. Then I'm going to go insert chart. And it didn't realize I wanted to scatter plot, so I'm just going to switch to that. I move this over a little bit, and now I want my trend line. So what I'm going to do is I go to Customize, Series, Trend Line. There's my trend line, and then as always, I want to label with my equation and show my R squared. So there's my chart. So my equation of the line of best fit, I can see it there. We have y equals negative 0.759 x plus 1539. There we go. And our R value, so we go equals coral, highlight my years, comma, highlight my y values, and we don't want this to autofill. And our R squared, we can see on our chart, is 0.326. Okay, so now what we want to do is we want to look at this data. So our R value is 0.57. So we have a moderate negative correlation here. So it's not bad, but it's not great. Our R squared is 0.326. So 32.6 of the variation in our y's can be determined by the variation in our x's, which isn't great. And if I look at my data, that line isn't a real representation of what's going on. So if I look at the data, there's a trend for sure, but maybe it's not a line. And sometimes this happens with our data. Sometimes a line isn't always the best way to represent our data. And sometimes a different curve could be a better representation. So what we're going to do is we're going to do a regression, but instead of using a line, we're going to use a different type of curve. And this is called a polynomial regression. So a polynomial just refers to a different type of equation. So instead of just being a line, it could be a parabola, a cubic, if you've taken functions, but it could be an equation as a squared, a cube, maybe something to the power 4, something like that, but basically just a different type of curve. So what we're going to do is we'll do a polynomial regression this time. So again, highlight my data, insert chart, and there's my data. Again, but this time around, I want to do a polynomial regression. So everything has been the same up until this point, right? I graphed it, I went to Customize, Series, nothing new. But now here, what I'm going to do is I want to add my trend line again. But instead of it being linear, which is the default, I want to change it, and I'm going to change it to polynomial here. And what it's going to do is I can change my polynomial degree here to the one that fits best. For the most part, we'll typically be looking at a quadratic, so a polynomial degree of 2, but it does kind of depend on your graph. But you can play around with them like that. Typically, we'll just stick with quadratic, but you can try other things if you'd like to. Again, you can change the line opacity, thickness if you want to make it look different. And then I want to add my equation as well as my R squared. So now we can write out our equation of best fit. So now instead of having that linear equation that we had before, just going to extend this so we can fit the whole equation there. We have 1.04, that E means times 10 to the power of, then we have plus negative, which is minus 1048x plus 0.263 x squared equals y. Now we have our r squared again, which is 0.929. Now the reason why we don't use a r value here is that's calculated from the actual data. And it's based off of a line when we're finding an r value. So when we're looking at polynomial correlations, we just focus on the r squared value. So you'll notice here in the chart, there's no need for an r value. So we'll just look at the r squared value. But when we compare our r squared values, this one is much better. Having 92.9% of the variation in our y values come from the variation in our x is huge. So part C, which one's more accurate? Definitely our polynomial regression. Based off of our r squared values, for sure, based off just visually looking at it, a much, much stronger regression. So up to you which one you want to use for your data. For the most part, lines should work for your project, but the odd time, one of these does work better, and you want to justify why you chose what you did. So there's our first example. Let's try another one. So for example 2, we're going to do the same thing again. So we're going to use the data below to complete a linear regression. So similar type of data. So first thing we always do is we want to start with linear. So whenever you're doing your regressions, start with linear first, go through it all. If they're seeming a little funny, then you do the polynomial one. So let's do that. We highlight our data, insert chart. There we go. It knew we wanted a scatter plot, which is great. Now I'm just going to customize, series, add that trend line, and we'll do the linear one first. And we'll show our equation and our r squared. So our equation of best fit, I'll just extend that just so a little bit easier for us to see later. Negative 0.62x plus 1263. We also have our r squared value here, 0.285. Not great, not the worst, but it's pretty low. And then for our r value, we do equals coral, our first column, second column, and close that bracket. So negative 0.5337. Again, moderate negative correlation. Not terrible, but not great. If I look at the actual graph, I'm noticing that the line's not really going through the data well. We also kind of see things pop up again at the end. So maybe this one isn't our best option. So what we'll do is we'll try a polynomial regression instead. So highlight our data, insert our chart. There it is. Again, customize series to do the regression, trend line. But this time around, I'm going to do a polynomial one instead. This one looks pretty good, having it be quadratic or a polynomial degree of 2. That looks pretty good. You can kind of play around with them, but they're all pretty similar. I'd probably stick to the quadratic, but you can try something different if you'd like to. Again, we label it using our equation and add in our r squared. Now immediately you can see a way better fit to this data. Right away we can see that the curve is going through far more points, a much, much stronger trend line. So let's fill in our chart, our equation of our line of best fit or curve of best fit. We have y equals 907,148 minus 912x plus 0.229x squared. And then our r squared, 0.885. much better r squared value here, so that's a great sign. Means that we've made a really good choice here. It also helps you to see that there is a relationship between these data sets. Sometimes when we have our linear trend lines like this, people tend to think, oh, there's no relationship here, and start thinking of maybe why that is. But maybe there is a relationship there. Maybe it's just not linear. And that's why we have to take these next steps. In addition, when you have a correlation like this, so when I'm using a quadratic or something different to form my trend line, I want to think about why things may have started to increase at the end. What trends, what things going on in the world with where this data set came from would influence my data to start looking like this. So those are the next questions that you want to ask. Okay, last example here. So for this one, a car skids in an accident, and the investigating police officer knows the distance that the car skids depends on the speed of the car just before the brakes are applied. So we have this data here. We have the speed and the length of the skid of the car. So what we want to do is we want to determine how related these two data sets are. So what we do is we do regression. We first start by doing a linear regression. So highlight the data, insert chart. Perfect. It was very happy with making a scatter plot. That's great. Let's customize it. Series. Add that trend line, and we'll go with the linear one here. Label with our equation and show our r squared. So our equation of the line of best fit is y equals 0.714 x plus, minus 10.7. Then our r squared, 0.928. So not bad at all, not a bad correlation. And what we also want to do is we want to find our correlation coefficient. So again, to do that, we go equals correl. Highlight the first set, then our second set. There we go, 0.96. So a really strong positive correlation. So here, this one's pretty good, right? Everything is looking really good here. But once I look at my data, I do notice that it's not really fitting a line super well. So although my r and my r squared are really good, I wonder if maybe there's something that could even be more accurate. So just because my r and my r squared are good, I often want to see if maybe there's something even better. So that's exactly what we're going to do. We'll go and we'll see if there's something that fits it even better, that it could be more accurate. So we'll do a polynomial regression, and we'll look at the different kinds of polynomial regressions, and we'll try to find the best one. So again, highlight my data, insert chart. Again, it understood I wanted a scatter plot, which is great. Go to customize, series, and let's add a trend line. Now, we want to switch to linear. Now we can do polynomial. That fits awesome. You can also try a few different ones. So you can try some to see which one is best. Polynomial definitely fits perfectly. If we look at that, it's almost exactly correct. That's a huge difference. Again, let's label with our equation and show our r squared. And if we look at our r squared, we have 1. That's a perfect r squared there. So that means this equation represents the data perfectly, which is amazing. That's exactly what we want. Which, although our last one was good, this is even better, which makes a huge difference. So we have negative 0.0161 minus 5.03 times 10 to the negative 4x plus 7.15 times 10 to the negative 3x squared equals y. All right, and our r squared is 1. So that means 100% of the variation in our y is because of our variation in our x's. And that is fantastic. Now what this means here is there's probably a real relationship, a real physics relationship between our speed and the skid length for a particular car for it to be this exact. It probably isn't random and there's probably more going on. But that's why this is so important, so I can tell if there is something more going on and that this isn't random at all. But that's the idea. So for your project, the takeaway you want to think about is you want to make it linear to start. But look at your data. Think to yourself, is that an accurate representation of my data? Does that make sense? Sometimes it really does, and sometimes it doesn't. In addition, sometimes you try a polynomial regression and it's nowhere near as good as your linear one, so that's the one you go with. But it does give you another alternative and another option to really see if there's a relationship between your variables.